Okay, today we're going to see the second part of the rectilinear kinematics, which is the study of position, velocity, and acceleration. Last time we saw the initial equations of motion. I want to remind you that we need those equations for the analysis of the position, velocity, and acceleration. So let's take a look at this example, this new application of those equations of motion. You see, erratic motion means when parts of the motion conform to uniformly accelerated motion, parts are not. How do you actually do a problem when you have both of those situations? So let's take a look and examine that today. Okay, so I'm gonna disappear from here. What's the velocity, position, and acceleration of particles or bodies, you may say, that are considered as one whole mass? And how do we use that using graphs? That's important because in accident reconstruction, we might have a situation where the vehicles um, skid, or they hit something else, or they skid on a different surface, or they roll over, or they become airborne. So in any of those situations, we have a different condition for different times. So and here we will talk about the position versus time, velocity versus time, and the acceleration diagrams that you can get versus time, or the velocity versus position, or acceleration versus position. This is based on the Hibbeler textbook. So here we go. We have a vehicle in here, a motorcycle, and this is the graph of the motorcycle that you have a different motion in here. If you have this position at 200 feet during this time, it started with the velocity 10 miles an hour, 10 feet per second, and the velocity change based on this equation. So you have a velocity change like this, and then you have from 200 to 400 seconds, the velocity is constant in there. So you have a variation of the velocity versus the position of on the first 200 feet. And then the question is, can we determine the acceleration at the position of 150 feet? So this would be in this location. So how should we do this? If we have here, we have this graph of the curve. We would have to use some basic calculus also, some basic position. For example, the position diagram, where is time and the position here, yeah? So if you have as a function of time the blue graph, you will see that the initial velocity is dsdt at t0. v1 at that position would be dsdt at t1. This would be dsdt at t2, and this dsdt at t3. So that way you can calculate the velocity. So if you plot this, the velocity versus time diagram can be constructed by finding the slope at various points along the curve. So if an accident reconstruction problem, you may have to work with the data that you have. If you have measurements, you might be able to reconstruct the motion, and that's the idea. You have measurements, or if you have, of course, the data from the EDR is the perfect one because that will record position and the velocity as well. From there, we can calculate other things. If you have the velocity versus time diagram, you know that you can calculate the acceleration, but you can, if you find the slope or the tangent to the velocity curve at any point, that would be the acceleration at that point. So on the top in here, we see if this is v sub 0, v sub 1, this is v sub 2, v sub 3. So the blue is the function velocity versus time. But the slope of this curve at different points is going to be the acceleration. So you see, this is a case where for this particular problem, the acceleration not necessarily is a constant. But in many situations in accident reconstruction, because the bodies are on a plane and the acceleration really in the vertical direction is the gravity, and that's the one that produces friction forces. So there would be a lot of problems that we deal where the acceleration is a constant or it is a fraction of the gravity. Okay, so that would be in situation for two cars colliding and skidding, for example. Then if you have the acceleration versus time, then it follows that if you are given this, then you will have the reverse problem. Instead of differentiating, you would integrate. So we can construct the velocity diagram from the acceleration diagram, and if we know the initial velocity. How do we do this? Because the integration of the acceleration diagram is going to give us the velocity diagram. It's going to give us the velocity diagram. The velocity diagram in this particular case would be obtained by integrating the acceleration diagram over an interval. If we have, let's say, the acceleration versus the velocity, excuse me, the acceleration versus the position. This is, of course, a little more complex. And the area of the acceleration, under the acceleration versus position, is the change in the velocity. See, remember that you could express the change in position and the velocity with the expression that you see in there. That was part of the derivations of the equations. We had this would be 1/2 of b1 squared minus b sub 0 squared, and the integral of ADS is the area under the curve AS. So this will allow us to solve for the velocity at any point. You could create a plot of the velocity versus distance if we have the acceleration versus distance. The velocity versus plot. So in this case, we could, if we use the graph like this, velocity versus displacement diagram, in this case, we could use the velocity, we could read the velocity v at any point on the curve and multiplying it by the slope of the curve. At that same point, we'll obtain the acceleration. So you see, whenever we have motion, there's a lot of things we could do to do this, to investigate and find out other terms. So for example, here, you are giving a velocity versus time diagram, and this is for a train that is moving between two stations. The question is find the acceleration versus time diagram and the position versus time diagram over this interval. This, it seems to me, it takes us in two directions, because right now what we are giving is the velocity diagram. How could we find out the acceleration diagram? We would have to differentiate this diagram, and we'll do that. But if we want the position versus time diagram, then we will have to integrate this. So we'll have to do it in both ways. Okay, so this is the plan. This would be in one case differentiate, in the other case integrate. So for the first 30 seconds, the slope is constant and is equal to dv dt, which would be 40 over 30 divided by, see, this is this section right here. Yeah, 40 over 30 would be the, like 1 point something is the slope of this curve. And you see it here. You know what happens over here? The slope is going to be constant. And then it's going to be negative on this side. So yeah, see here, constant, and the slope negative. So this diagram that you see on the screen will be the acceleration versus time. That's what this is. If we have the area, in this case, under the curve of the velocity, we could integrate this. Under the velocity diagram represents the displacement. So the area between 0 and 30 would be 1/2 of 40 times 30 divided by 2 is 600 feet. Alright. And the area between 30 and 90, yeah, that's uniformly accelerated motion, 2400 feet. And the area between 90 and 120, it will be 1/2 of 430. This is another 600 feet. So this would have the position diagram. Okay, we could take a look at different problem, but let's pause this for a moment.